So friend, we are into our 11th module or 11th week, and this is the last lecture of this week, and here we are exploring intelligent approach in support of optimization of risk conscious testing and maintenance management, RCTMM, risk conscious testing and maintenance management. Because we are talking about safety, so standby system, safety systems are standby systems, and that is where we have to see the effect of maintenance and testing. We have seen how it is done through traditional approaches, linear approaches with single objective function. Here we will see what an intelligent approach can provide in terms of benefit, in terms of space, and in terms of result itself, So let us go to the, there is a special tool in AI, it is called genetic algorithm. Genetic algorithm, the background is like this, it is inspired from our evolution, natural genetics and evolution, how the population, you have the population over here, genes, and then mating and selection occurs, and then the genetic phenomena happens over here. I'll summarize the whole thing here in phenomena. It's a biological phenomena which is happening at the human level. And then the best selection. So the bottom line rule is select the best and discard. Darwin's principle, So, and the new population comes, and this is how the genetic algorithm has been inspired. It's a AI algorithm, and where evolution, which is based on evolution theory, and GI is a heuristic and population based probabilistic search method. So essentially the nature of the problem is probabilistic in nature, and then there are heuristics also in this one. So so in the previous lecture, the test maintenance interval was based on the and the matrix was core damage frequency, that is risk. But here we will be taking a little complex matrix where how GA approach, it helps us because it is a multi-objective function. Multi-objective function means unavailability is one, cost is one, and radiation dose. So you might be thinking why we have not taken CDF, because we wanted to evaluate the system at ECCS, that is safety system level. So what are the objective function here? So radiation dose, even though it is negligible, it is negligible. I'm sorry, this is a thing here, negligible. So how it can be optimized? Earlier it was unavailability was the function, that we saw for, and then finally we translated into core damage and all. That was an open thing option. Now solution involves objective function, requires a approach that is capable of modeling randomness, one thing, to enable a global search such that the convergence does not get entangled in local minima. When the optimization is common, is complex, where multiple objective function is there, then where the minima will occur. Suppose if the first minimum occurs and the algorithm gets stuck up there only, it is not able to come out of that, because objective is global minima. It is happening in 3 dimension. Okay, so that optimum, then optimum minima is one criteria, but it should be the best solution. The best solution is, because if we look at the minima level, one minima may not agree with other minima, but there should be a optimum solution, and that is where the genetic algorithm works very effectively. So here our target is unavailability modeling that we have actually. Okay, then what kind of unavailabilities are there? We might simplify it later on, but then we should at least know what are the contribution to unavailability. If U is the unavailability, total unavailability, then it is a function of the random failures. Random failure means lambda, we use that term. So lambda into t, it is a random failure. Okay, then it is a testing failure. What apportionment of the time, normally it is characterized by tau, it is used, and test interval, TAC test interval. So a fraction of these two, let's say if I take only 20 hours for testing and test interval is 3 months, so fraction will come here. So this is a main matrix here, over here, and then human error. Human error also causes unavailability. So this is the model for human error. Okay, this is the model for W is the model for unavailability due to aging, and D is related to degradation. They have been taken separately, but okay. So these are the models that are available. Now, if I start doing with this, the problem will become very complex. Now, point number 1, and point number 2. In my operational domain or maintenance domain, these two things are more important. Human error can be part of this when it is playing a dominating role. As I told you, plant is not showing any aging signal, so degradation signal. So, and human error is the one which can be directly monitored, and there was no, in the test data, there was no. So, if you want to go, you can go with this model, but for the practical purpose, what experiments were, simulations were done, we did with this only. And in here also, sometimes we have not considered this part, as I discussed you in the previous slide. So, in applied domain, modeling a problem, it requires a sense of what is the domain knowledge that is required and what is expected from the analysis. Okay. So, the complete model is available for you to take it, but for me, finally what it matters is half lambda t, that is unavailability due to testing and demand related failure, and which can be approximated, I am assuming it can be approximated to half lambda t. Okay. What I am telling here is the failure might have occurred. I don't know when the failure has occurred in the latent state. So I am assuming it was the average of the time I have taken t by 2. So any time it would have taken, and it is a well accepted assumption. So half QD is equal to half lambda t is the assumption which is based on the practical methods and whatever models that are available we make. So unavailability modeling we have seen. Now cost modeling is how much cost is required per testing. So cost per testing is equal to testing of cost per testing means it is the cost involved with each testing. So you will get the number life of the plant and then T. So if I assume certain life of the plant and then again T is the this thing, and L is giving us average life of each component, because finally you from component you build the plant actually. So it will be summation of all the components that we have over here, and then finally the practical way of having it is here. CT means cost per testing is equal to nothing but average cost of human we call man hour required, and then number of mans that are involved, and tau is the time required in so what is the accumulated time required here. So this gives me the cost modeling. Okay. So then finally we have is dose consumption. So dose consumption means it is known that it is not that warning, but since we are talking in an open forum, we can consider this as a dose consumption model also, because in the high radiation area this could become a limiting factor. Okay. So dose consumption per testing is nothing but whatever is the minimum consumption per testing and then expected life of the plant divided by the test interval. We will get this model appears like this because we are basing this model based on the plant data that is available. So we have these three models. Had it been a classical approach, we would have been considering minimization of Z. Z is a function that is unavailability, let us say, if we talk about it. Then one component, second component, third component is a linear equation we have here. But its limitation is it cannot handle multi-objective function, the way issues we are talking about, in the so here everything is into talked in terms of unavailability only. So power of GA. is complex multi-objective function through algorithm GA approach. An operating mechanism, as it is based on the random selection. Randomness or probability is the key element of this approach, because the first criteria is selection, then crossover, and then third is mutation. We'll see in the next slide how they operate. So GA approach has been used here, and it is I would say R&D component of this lecture. Genetic algorithm has a very powerful tool for optimization. It will not be completely correct, because optimization, instead of optimization, if I use the best solution, so that will be more proper, because it is not optimizing a individual space. It is looking for a optimized space among the optimization parameters. So the best solution will be the right term for this. Computer science and operational research genetic algorithm is a meta heuristic inspired by the process of natural selection that belong to the larger class of evolutionary algorithm, EA. Okay. Then finally we have it is used for high quality solutions, because as I said, the best of the best is selected during each stage of GA, and then finally a best solution, or it is called elite solution, is found, because the algorithm operates in a manner, it is telling itself that you are giving the best solution, elite solution. The optimization problem deals with the multi-objective function, and genetic algorithms have been shown to be effective. Intuitively, GA starts with a random activation of solution in the solution space. So in this technique, we have used real value genetic algorithm. That means we have used real data. That means we had the data available with us, past data, as I have seen I showed you in the past thing, and those data, so real value data were used, and they were converted into the 0110 strings, where the selection starts, crossover starts, and mutation starts. And finally, the data is characterized like this, and one change anywhere, it is called mutation. So you are brought a new spring, actually new offspring, and different terms which are associated with of course our objective function comes here, and then encoding the data in this way, and then check out constraints, what are the constraints that are there, identify input parameter and fitness value for mathematical formulation, and finally again decoding to our normal value. So it is called real value genetic algorithm that has been used over here. Modeling GA for multi-objective function, yes, for ECCS we had so many parameters like unavailability, which is contributing to availability, is resources, radiation, dose, and 3 functions we have used here, and real parameter algorithm was adopted for this particular study. The present assignment can be classified as a search application for GA has been used to optimize multi-objective functions, okay, and it is applicable to engineering system, particularly safety system application over here. Now, the terms which are associated here, because we will not be going into the specific module or which kind of functions or sub-functions have been used, we will understand that deeply. So first item is search involved determining solution to be that needed to be preserved and allowed to reproduce. We are using that language of genetic evolution. Once deserve to die out, okay, and then crossover. The operator is used to create new solution from the existing solution. That means the string will be modified in the mating pool. A probability of crossover is also introduced in order to give freedom to an individual to solution, so to determine whether the solution would go for crossover or not. So that means second stage criteria, stopping criteria has been developed. At the same time, a newness in the crossover which has taken place, mating it has taken place, a element was created. Mutation is the occasional. It is not a uniform thing. Introduce a few new feature to the solution string of the population to maintain diversity in the population. Because we say that we are inheriting those characteristics, but while inheriting the characteristics, there is some newness, it happens in the genetics, and that is what the mutation brings out here, and this happens here based on the random processing. And then encoding and decoding. Of course, encoding happens before the start process, then encoding and decoding happens, and last is elitism. Elitism is the preservation of few best solution to the population, and this is where the turning point we have, that we get a very good solution. Optimum is good. We are very near to, we have taken a balanced way where it is satisfying all the objective function, but it is and while giving the best estimation. So now whatever ECCS the problem was mapped, then performed. I will not go into the details of the problem, it will become a long presentation. The results were like this. Using this procedure, the 3 parameter availability, mineral consumption and cost have been optimized, and these are very important things in surveillance test interval and maintenance optimization. All the failure probability data for the system components along with the crossover mutation, so they were taken from 0.6 to 0.01 respectively. All the failure probability data for the system components along with the crossover and mutation probability. So these are the mutation probability, this is the crossover probability, and this is the mutation probability that we used in our genetic algorithm, and this we were discussing in the previous slide. Population size of 30, because 30 components which mattered were taken into this GA modeling, and GA algorithm was able to find the optimum value of STI uniformly over the Pareto front. So Pareto front is one of the technique that probably we used, and I think we used many front, but we found for this specific problem Pareto front was better. With enumerated method, it has seen that cost minimizes at STI value of 9490. Now you know 8760 is the number of hours, that is 365 multiplied by 24, you get 8760. That means our algorithm, if we consider cost, but in nuclear and safety-critical system, cost is not a constraint actually. It is unavailability as the constraint. So 94, you got a better space. But with this problem, this cost has gone out of this thing because we were canvassing our case. Our change case was for 6 months, from 3 months to 6 months. So that shows what kind of margins are built into our system. From cost point of view, had it been an industry, normal industry, they would have accepted annual testing because 9490, but in risk critical, safety critical system, the margin is very high, and that is demonstrated in this case. So even if I go for 6 months, it will be okay, this half of 8760. So minimum mineral consumption occurs at the 10,000 hours. That is also much higher, because as I had indicated, even through a common sense tell that mineral consumption is not a constraint, you know. So what is happening here is, in our result, all our mental model, our stipulations, they were meeting, and as we say normally, the human factor or expert judgment is very difficult to or they are very useful. Conversely speaking, I will say they are very useful for design and all that. So now if outage time is included, then you see what we pay. If SI is part of the calculation, where it is assumed that the plant is under normal operation, and then we have 7685. Still we have a margin, because 8760 half, and we are still having margin, and the probability, the unavailability is again. So we have to take a decision from based on the matrix. So we are very closely, we are coming to that we can have 6 months, okay, because 5 to 3.5 is not also very high. If we have 10 to the power 1 is high, we can work upon the system redundancy and all that, we can go upon that, but that is up to the organization. If testing time is STI term is excluded, if it is excluded, then we have this one. If it is include this, and if we exclude this, so we have STI value is 231 is this one 6.3 10 to the minus 5. Okay, so the unavailability is low. STI value is survey test interval is 231. So we have seen the upper bound, lower bound both here, and now we will see in the graph how how these values are varying. Okay, so we have when excluded testing time is excluded, we have 1, and testing time is included, and then we have a host of values over here. And then if you plot it in the graph, you can see the graph is minimum consumption and STI, and then here it is unavailability. For us, unavailability was the maximum given weightage over here. So minimum cost of STI is 9492. Okay, what is the unavailability? 2 into 10 to the power 2.002.9. That means almost 3 into 10 to the power minus 3. And we can have it, but suppose in between if we want to go, so we are having this figure, and then my cost is also minimum. So this is for the case 1, excluding testing time. Testing time we have excluded. Now again graph 2 is also for excluding the testing time, and in the next two graph we will see if we include the testing time what happens. And 9490, you see all these figures are comfortable here. And the maximum cost at STI is equal to 100, actually that is what we have, 100 hours if we take, Now case 2, including testing time, if we include the testing time, then availability and minimum consumption, and then we have maximum STI is 401, and the minimum cost at STI is this one. So you can see all the parameters, unavailability, cost and minimum consumption. Actually this graph should have been presented in 3 dimensions, but the objective here was to explain you the relationship. Otherwise a 3D graph would have been better, wherein unavailability, minimum consumption and cost, these 3 are playing 3 axis x, y, z. You can see here also, you can see that here it was taken that maximum cost of STI is coming over here, and then we have unavailability at 10 to the minus 3, might be 5 into 10 to the minus 3 might be acceptable figure, but STI cost is STI is 9498 minimum cost at STI. So the costing. So here this graph is being presented in terms of a parametric study, but we have got very beautiful insights on this. We can go on working further. This was a R&D project, and we can work on application model of this plant, and results are at the end of the day very encouraging. So we have seen limitation of the linear approach, role of genetic algorithm, maintenance, modeling aspect, plant consideration, results and discussion. So this particular case study and previous case study, why even this lecture itself was part of one chapter of my book, that was risk conscious operation management. You will find all the stuff there. This book was published in, I think this is one paper was published in Columbia, USA, and then that time I was working on risk conscious operation management book, and that book was published in 2023. Okay, so this was one paper which is part of this. At the outset, I would like to tell that the information which has been captured in this chapter on risk conscious operation management is from generic sources. Most of the information is from generic sources, and that becomes a sort of, then there is a book on risk based engineering, which Professor Pett from University of Maryland, when I was visiting faculty there, so there also is, it has been, this particular lecture has been inspired from there, and then we have, this is the paper, and I would like to remember my student Shaumik Chaudhary, and he worked tirelessly on this risk surveillance test interval optimization, and major part has been, and he presented, of course he has not presented, I had to present it. I don't have my friend with me now, very unfortunate. But then he was the force behind developing this particular genetic algorithm approach, and he did a very good job. I thank you him, and I wish that wherever he is in peace. And then we have other papers, of course. So, but then in my book on risk concentrated operation management, this has been there. This particular chapter is there, and all the material will be you will find there. Thank you.